the next speaker is Kevin. He's an assistant professor at MIT in the electrical EECS department. So Kevin and I both worked at Harvard for, we have some overlap at Harvard. I think we have been discussing how to develop really useful soft robots to solve real-world applications. Also, I think what's really impressive, what he has been doing is he always developed this kind of very novel robots for underwater or aerial applications with high impact and also published in high impact journals. The stage is yours, Kevin. Thank you.
Okay, great. Thank you. Can you hear me and can you see my slide?
Yes.
Okay, great. So let's get started. So today I want to talk about micro aerial robots powered by soft artificial muscles. Now there are two keywords. There are micro and soft. So I'll talk about micro first, and then we're going to move on to soft later. So first of all, I just want to motivate or set the background of what are micro robots. When people think about robots, we usually think about large-scale robots, such as humanoid robots or even trains or airplanes that spans the scale of meters to the order of hundreds of meters. On the other end of the spectrum, we can also think about very tiny robots made of the MEMS technology. They usually range from tens of microns to hundreds of microns. What I want to focus on today are insect-scale robots, and more precisely, they range from 1 to 5 centimeters, and they weigh from 10 milligrams to 10 grams. Very quickly, I want to give an example of microrobots. While I was doing my PhD at Harvard, I worked on a microrobot called a RoboBee. Now, this robot weighs 80 milligrams, and its flapping frequency ranges from 120 to 260 hertz, very comparable to a real bee in nature. So now, I want to address several important questions together. The first one is, why do we study microrobotics? To me, there are two reasons. The first one is that using microrobot, we can achieve functions that are challenging, if not impossible, for larger traditional robots. For example, here we teach the same microrobot to both fly and swim. And the second motivation is that using microrobot as a platform, we can investigate interesting physics at the centimeter scale. By looking at a flow field generated by a flapping wing robot, we can infer about the lift and drag generation mechanism of a flying insect. So today, I want to talk about 3 major projects, and I want to focus on the last one primarily because the theme of today's talk is on soft robots. But first, let me just set the background and show you what the state-of-the-art rigid microrobot can do, and then I'm going to move on to talking about soft actuated robot and why are they important. So in the first project, I'm going to talk about a hybrid aerial-aquatic microrobot. So in this robot, the goal is to enable a very tiny robot to do multiple things and to transition in very complex environment. Specifically, we want this robot to be able to take off from land, hover in air, transition from air to water, swim in water, transition from water back into air, and also land on ground. There are a lot of things we want this very small robot to do. And again, let me just skip over all the implementation details and say that in the end, we are able to create a 175 milligram microrobot that is able to take off, fly, and hover, that is able to swim in water, that can transition from air to water, and more impressively, using a microcombustion to impossibly jump from water into air and also passively land on ground. So for the first time, we've demonstrated that a 0.1 gram robot can demonstrate multiple things and move in multiple environments. And some of those functions are challenging, if not impossible, for larger traditional robots. Following the same thread of thought, we move on to develop a hybrid terrestrial-aquatic robot. And again, the goal is to teach this robot to move in multiple environments and to perform multiple functions. More specifically, in this case, we want the same robot to be able to work on land, work on the surface of water, move on the surface of water, controllably transition into water, and sink into water, and eventually return back onto land. So again, doing multiple things in a small platform. So now I'm going to show you a video. So this robot starts on land, will move onto the water surface, and now this robot swims on the water surface, and it will swim to a target site. So now I recommend you to focus on the side view of this video. Okay. Once the robot swims to this targeted site, it will sink into water. So now it's completely submerged under the water. And we will command this robot to climb this incline and slowly return back onto the ground. In this transition process, the robot also has to overcome a surface tension force that's about 2 times the weight of the robot. So again, we've shown that in a very tiny platform, this robot weighs about 1 gram. This robot can transition between multiple environments and perform multiple functions. For those of you who cannot see the video clearly, I'm showing you a composite image that pretty much show you the same experiments. The robot starts on land, swim on the water surface, sinks under the water, climb this incline, and eventually return back onto land. So as a quick summary, what we've shown in rigid microscale robots is that those robots are multifunctional and agile platforms that they can do multiple things and move in multiple environments. But today, I want to introduce to you a new type of microrobot, which is a microrobot powered by soft artificial muscles. And let me motivate why this is important. First of all, I want to tell you about our longer-term vision, which is to create a swarm of ubiquitous, multifunctional microrobots. Up until now, all the microrobots that I have introduced involve only one robot operating in isolation. It's very fragile robot that we don't want it to collide with the environment. But in the future, if we want to mimic insect, you really want a large swarm of them to collaboratively accomplish a task. So let's think about the challenges and opportunities that current microrobots face. So far, I've shown you that a single microrobot operates at a high bandwidth, higher than 100 Hertz, and they're very precise. My colleagues at Harvard are solving key problems in microrobotics in that they're looking at putting lightweight, low-noise sensors and controllers on board. They're also thinking about control circuit and batteries. However, there are still some key questions that are very difficult to address, namely that microrobots are usually powered by piezoelectric actuators, which are very fragile and they have very small strength. And as a consequence, they're not as robust as insects. And in addition, because they have very small strain and they're very fragile, it's very difficult to make a lot of them. So that's why we couldn't operate multiple microrobots in the same setting. So how do we address this problem in microrobotics? Well, I propose we look into a different field, which is soft robotics. For very long, people know that soft robots have large strain and they're robust. They can safely interact with the environment. And we know how to make soft robots effectively through either casting or even 3D printing. In terms of control, most soft robots are controlled open loop and they passively interact with the environment. And in addition to using a battery, soft robot can also be controlled pneumatically or chemically. However, soft robot also faces key challenges. For example, most soft robots operate at a low bandwidth, typically less than 50 Hertz. And in addition, because they have large strain, they usually have low precision, which means controlling them becomes challenging. So how do we solve key problems in both fields? I propose we look into a new direction, which is called hybrid soft rigid microrobot. The idea is that we are going to power future microrobot by robust and high bandwidth soft actuators, but we still will put in rigid appendages for effective interaction with the environment. A preliminary example I'm going to share with you today is a flying microrobot powered by a dielectric elastomer actuator. And I want to convince you of several things. First, this actuator has a high bandwidth, can operate on the order of 500 Hertz, has large strain, has a strain on the order of 10%, and it's very robust against collision because of the nature being soft. And in addition, in terms of fabrication, we incorporate both the soft actuator, which is very easy to make, this very precise rigid parts, such as the robot transmission and the robot wing hinges, so that we can achieve very precise flapping wing motion to generate lift and drag forces. And in terms of control and sensing, not only have we been able to show controlled flight, we also show that we can use the soft actuator as a sensor. Whenever the robot collides with its surrounding, we can sense the collision by detecting the change of capacitance of the soft actuator. So let's talk about the robot in more detail. Our robot is made of a soft actuator, an airframe, and the soft actuator is connected to a connector, which then connects to a linear 4-bar transmission. And this transmission is then connected to a wing hinge, which connects to a wing. The core innovation of this project is really the soft actuator. So first, let me explain to you the state-of-the-art rigid piezoelectric actuator. This actuator operates at a high bandwidth on the order of 1,000 Hertz, and it has very small motion on the order of 0.2%. And as a consequence of this small motion, it requires very precise manual assembly that usually require a precision on the order of 10 micron. Instead, we have came up with a dielectric elastomer actuator that's rolled into a cylindrical form. This actuator can operate at 500 Hertz, has a very large strain comparatively on the order of 12%, and because it is soft, it's tolerant to assembly error. So the precision that we require is reduced by a factor of 10 to the order of 100 micron. So now let's think about what requirement do we have on the soft actuator such that we can achieve takeoff flight. If you're interested in the details, please read our paper. But let me say that a few scaling arguments can set the performance metric on those actuators. By requiring the lift force of the robot to balance the weight, we can have a performance metric on the bandwidth and free motion of the actuator. And in addition, the block force of the actuator has to fight against the drag force, so that we again have a requirement on how much force the actuator must acquire to enable flying motion. And finally, we also have a certain requirement on the inertia of the wing, which enables the robot to operate at a certain frequency. In terms of the actuator, there are 3 key parameters: the bandwidth, the free displacement, and the block force. So I'm going to explain to you how we measure and quantify those parameters. So first of all, let me just go through the principle of a DEA very briefly. The principle of a DEA is very simple. You put on 2 layers of compliant electrode and you sandwich them in an incompressible soft elastomer. Then you put charge on one of the electrode. The electrostatic force pushes on the soft elastomer and causes the elastomer to expand in the other 2 directions. And we use this deformation to do work, to push on the transmission and enable flight. And we adopted a multi-layering process in our work. Namely, we start with spin coating a soft elastomer, and then we transfer a certain pattern of carbon nanotube as the electrode. And then we repeat this process. So we keep on layering elastomer and thin electrode until we get a multi-layered structure that has a lot of layers of thin electrode and elastomers. And then we cut the elastomer out from the template, roll them into a cylinder, and put top cap and bottom cap to make them into a cylindrical actuator. So now let's talk about the performance metric. The first performance metric is the bandwidth. Turns out that the bandwidth is proportional to many parameters, proportional to the electrical property of the actuator, which we can simply model as a linear RC circuit, proportional to the mechanical property of the actuator, the material damping of the soft elastomer, and it's also proportional to the geometry of the actuator, namely how long and how wide it is. For our system, we have been able to achieve a relatively low resistance and a relatively large capacitance in such a way that we can obtain a RC time constant that's on the order of 0.2 millisecond. And this allows us to have a resonant frequency that's on the order of 500 Hertz without any load. The second parameter I want to talk about is the block force. To characterize the block force, we compress an actuator under a 9917 titanium force sensor, and we measure the force from the force sensor. And for every measurement, we take the 0 to peak value, and we map them onto a larger plot. So for this plot, we vary the actuation frequency and the actuation voltage, and we can obtain a map that characterizes the actuator performance. The peak performance of our actuator shows that our actuator can exert a block force that's on the order of 0.2 Newton. And the third aspect is the free motion. So again, we place our actuator under a laser vibrometer. We actuate our actuator, and we use the laser vibrometer to measure the oscillation motion of our actuator. So in this case, we take the peak-to-peak motion, and again, we map the peak-to-peak motion into a particular point, and we repeat this experiment for different actuation voltage and frequency. So as you can see, the resonance of our system is around 500 Hertz, and the maximum free displacement that we get is on the order of 1.2 millimeter. So with the free motion, the block force, and the bandwidth, you can compute the energy density of our actuator and also the power density. Notably, we have achieved a soft actuator that has a fairly high power density on the order of 600 watt per kilogram, which is about 60% of the piezoelectric actuator. And in fact, from our scaling analysis, we show that as long as you have a power density that's higher than 200 watt per kilogram, we are able to achieve takeoff flight. So now let's think about the robot. We incorporated our soft actuator into the flapping wing robot, and we've shown that at a flapping condition of 300 Hertz and about 1200 volts, the robot is able to achieve a peak-to-peak flapping angle on the order of 85 degrees. And by looking at the flapping wing kinematics, we can infer about the lift and drag forces. In this case, we measure that the lift force is on the order of 1.2 times the robot weight. So we are very excited by this result, and we want to demonstrate takeoff experiments. So here I'm showing you two takeoff experiments. In both cases, you see that for the first time, a soft-powered robot is able to take off from land. And it was a very exciting moment for us because it demonstrated a soft actuator have high enough power density to enable lift-off flight. But on the other hand, as you can see from those videos, with one actuator, the robot is not controllable. And because a flapping wing vehicle is usually intrinsically unstable, this robot quickly pitches over or rolls over and falls back to ground. So practically, from a robotic perspective, it's not a very useful robot. For those of you who cannot see the video, I'm showing you a image sequence that shows the same experiment. Effectively, the robot pitches over and falls back to ground in 0.1 seconds. So it's not very useful. How do we stabilize this robot? Well, we can put two units together. And in this case, if we can use a phenomenon called precession, that is, if we can allow the robot to yaw very quickly, we can use this fast spinning motion to stabilize the robot. Intuitively, that's very similar to a spinning top. Now, to ensure stability, we have to look at the contribution of the yaw torque and the moment of inertia tensor. So for the interest of time, I'm going to skip over the mathematical proof, but let me just show you both experimental results and simulation results. So in both experiments and simulation, we've been able to show that our microrobot can take off and they can fly upward without any sensing and feedback control. In fact, the ascending speed in this case is on the order of 30 centimeters per second, which is even faster than the state-of-the-art robot powered by piezoelectric actuator. For those of you who cannot see the video, I'm showing you a composite image of the same experiment and simulation, showing you the takeoff of our robot. So now I've shown you that with one unit of our robot, we show the robot can take off, but is unstable. With two units, we show the robot was able to achieve passively stable ascending flight. The ultimate question for soft robotics is that are soft robots controllable when they operate at a high frequency? So again, I'll just skip over the formulation of the controller, but just say that with a very simple PD controller, we are able to demonstrate controlled hovering flight. So in this case, this robot is able to fly very similar to a quad rotor and is able to fly at a set point. Okay, this is a very exciting and important result for us because it shows a soft robot can operate at a high frequency, have very high power density, and also is controllable. So for those of you who cannot see this video very clearly, I'm showing you an image sequence. Essentially, this robot takes off and hovers at a set point that's about 10 centimeters above ground for 15 seconds. And that translates to 4,500 flapping cycles. So again, if you look at the trajectory, the robot takes off and hovers at a set point. The air in the z direction is on the order of a centimeter, and the drift on the x and y plane is on the order of 3 to 4 centimeters. Again, this is achieved with a very simple PD controller, and we definitely look forward to further improving the hovering performance of our robot. Now I've shown you that our robot can demonstrate what the state-of-the-art robot can do. Let's think about what additional benefits are there. The first benefit is that the robot is robust against collisions. So you can repeatedly collide a wing with an obstacle, and because the actuator can sustain large strain, it's actually robust against those kind of collisions. Something very challenging for the piezoelectric driven robot. And in fact, you can monitor the change of current to detect the collision. And the principle is that a collision will cause a local deformation of the actuator, which will cause a change of capacitance. And we can pick up this change in capacitance by monitoring the current. And we can use this technique to detect in-flight collision. In this case, we deliberately fly a robot and fly this robot into a wall. As soon as the robot makes a collision with the wall, we can detect that collision by looking at the instantaneous current that we see from the actuator. And this robustness and the capability of collision sensing, we can also demonstrate collision recovery. In this case, we are just demonstrating a very simple passive recovery. The robot takes off, collide with the rim of a cylinder, and continue to fly upward. Now, I've shown you a video, and I can also show you the composite image of the same experiment. This is a very simple experiment in the sense that everything is passive. We just want to demonstrate the robot can survive this collision and passively recover. Something that we are doing right now is to demonstrate the robot can actively run into something and recover from in-flight collisions. And in addition, we mentioned that soft robots are very robust. So for the first time, we are able to fly two of them together. And in this case, just to have some fun, we intentionally run both robots into a wall just to demonstrate that they're robust against collisions. If you think about insects in nature, they constantly run into their environment, collide with obstacles, or even collide with each other, and they survive. So that's something that we think is very important to do to be able to study swarm behaviors in the future. And in fact, we can even fly two robots into each other. In this case, you see that one robot tried to push down on the other, and again, those robots experience no damage. We see that as a huge benefit in the future for studying swarm behaviors. So in terms of future work, we are now exploring new configurations. For example, something we are considering right now is to create a multiple wing robot that looks like a dragonfly. And the hope is that use this configuration, we can study new phenomena such as forewing backwing interaction and use this robot as a prototype to study dragonfly flight. And in addition, we are not limited to dielectric elastomer actuator as our soft actuator. In collaboration with Professor Rob Shepard from Cornell, we also developed a flying robot that's powered by a pneumatic soft actuator. Again, very counterintuitively, we can operate this robot at 165 Hertz, so very high compared to what people think that soft actuator can operate. And the other thing that we can think about yearly is think about swarm flight in the future. Now we can make one microrobot very cheaply, and they're very robust. Can we make a lot of them and have them collaboratively demonstrate things that are useful? So that's something we are looking into. And I've already shown you that the state-of-art rigid microrobot can do multiple things and in multiple environments. We definitely look to extend this type of functionality in soft-powered microrobot. So hopefully our future versions of microrobot can not only fly, but they can also perch on a tree branch. So with that, I'm almost at 25 minutes, so I'll end here, and I'm happy to take questions. Thank you.
Hey, Kevin, very exciting talk. I think we have time for one question. So
Okay.
basically, usually DEA require very high voltages. And how do you power these devices? And do you have a plan for including power on board?
Right, so power is definitely one of the very important questions that we are thinking about. So currently, our actuator operates on the order of 1.2 kilovolt. Now, we are definitely looking at ways to continue to reduce this operating voltage. One of the ways that we are thinking right now is to increase the spin coating speed, and the target that we are trying to get to is to reduce the operating voltage to on the order of 500 volts. So if we can operate the robot at about 500 volts, then creating onboard circuitry and incorporating onboard battery becomes feasible. So achieving power autonomous flight is definitely something we are looking at and will work on in the future. Thank you.
Very cool. Yeah, thank you. Yeah, due to the time limit, let's switch to the next speaker. I think Dr. Kabila, could you please